So here what basically we will try to understand, we'll try to understand the Python code by which we have implemented the gradient descent that we have just seen as a theory. As it's a very, it's a code from a scratch. Okay, so that's why there is no specific function I have used. So let's try to understand what exactly it is. First thing is that you see there are two things here. There are two functions actually you have used, not two functions, three functions. Compute error for line given points, then the step gradient, and the gradient descent runner, which is basically occurring for the gradient descent algorithm. So you see, if we start from the this particular function, what it is doing basically, as I told you, that it is basically finding the error, right? So error of each and every data point. So let's see first of all how many data points I have. You see, the data points I have taken from this particular CSV file, first of all. So let's just print the points here and try to understand what exactly it is. So before that, we have to import these files. Fine. And then now we will run this particular line, and you see this is the say some instance of lot of x and corresponding y. Okay, so this is my actual y present in my data set. Now what I will do, I will actually try to find out the optimal value of m and c, for which I will get the predicted y which is very close to this actual y's. That will be my intention, so that for any unknown x means, for example, some x, say x equal to 25.3, this 25.3 is not present in the dataset. But if I have the straight line, just I will put the 25.3 in the equation of the straight line, I will get what should be the corresponding value of y. That is what benefit we will get. So this is my data, a synthetic data. So let's now see what basically we are doing here. First of all thing is that what we have passed here, we have passed here b, m, and the points. The points mean the points, that's what you have seen. And what is this b and m? B and m is nothing but the intercept and the slope. But remember, the intercept that we are saying, that the c basically, in machine learning, that is what we call bias. Okay, so what is the significance of bias in in further we will try to investigate in other complex models. Anyway, so let's do one thing. Let's see what exactly, how exactly we're doing. We are actually just, it's a very simple code, I think. So just error is equal to 0 initialized, and we have a for loop here. What is this for loop is doing? This for loop is first of all collecting the the actual y by from these points, right? And it is trying to find out the predicted y by this equation mx plus b. It's nothing, b is representing c actually. I mean, in my theory what was c, it's written b here, so it's nothing but equation of straight line. I hope you can easily understand, right? So this mx plus b is representing the predicted y for every x's, start for every x's in the range 0 to length of the point. That means for all the points we have the x's, that x we have found here, and that x we are using here to find the corresponding y, I mean for predicted y. That predicted y is subtracted from the actual y, and these two things is basically squared over here. Just I am following the equation that you can see in the, you have seen in my slide. So remember, the square term we represent in Python by double star. Okay, single star means multiplication, double star means square. And you see, this is nothing but I am basically adding. Total error is adding like this. Total error plus equal to like this. Adding. But what do we require? We require average error, right? Ultimately. So this average error is nothing but total error by total number of points. So that's why just it's given float of length of points. Okay. So typecasted to float so that division can be done properly. So as a result, this particular function is actually returning the average error between set of points and predicted points based on a particular straight line represented by a particular b and a. Now next come to the step gradient part. What it is doing? This is what exactly doing the this is the implementation of the steps that you have seen at the end in the last slide. Like you see, this particular line is nothing but is that particular implementation of the equation that you have seen in the slide, that minus 2 by n into y minus the m current, that is the m into x plus b. If you can recall what you had, you can easily get that. Anyway, let's do one thing. Let's just go back and check whether this one is correct or not, what you had. See, this is the two equations that we have just observed in the code. Over there, that minus 2 by n, because this minus will come out from the summation sign. So that's why minus 2 by n. Then summation over means it's a for loop. If you try to make a code for this particular line, it's basically summing over this particular equation for every I. So summing over means what? It's nothing but make a for loop for each and every points of xi, find the result and add it. Similar for this one, right? So let's do one thing. Now let's go back again. Okay. So this is the two, the corresponding Python code that you have just seen. I hope this is now clear. And then you see, I have calculated the new m, the new value of m by this equation. This equation also you have seen in the slide. That is the some new, here it is new b. New b means the b current minus learning rate into b gradient of the b. That is the delta b. Delta c in my slide, if you can recall. Whatever it is written b gradient was delta c in my presentation. Whatever is written as m gradient was delta m in my presentation. That is the thing. And it is doing for all. You see? So this is what there, this particular, as a result, what this particular function is returning? This function is returning that new b and new m. So this is step gradient function. Okay. So now we will see what exactly this gradient descent runner is doing. This is nothing but actually, iterating over, with all these functions that we have seen, which is basically, you can assume like the outer loop. It's like, you see, we will start with a starting b, which is nothing but the initial b, arbitrary b that already we have seen, an arbitrary m, and some level of number of iterations that also we have to decide, that we will go for 100 iterations. How many times we will you will go through the chapter. That you have to decide before learning, right? Say for example, you want to go through the particular chapter 10 times. You will read for your proper learning. Or someone else may decide that I will try with five iterations. And 5 times I will see some chapters. Similarly, here also you'll have to go some number of iterations. So in the first iteration, what we will do? With this starting B and starting M, we will basically try to find out what should be the corresponding new B and M we will get, right? And that's why you see this state gradient function is calling, which is just written here. Sorry, here. So in this state gradient function, if you see, okay, so which is basically passing the points and the learning rate, which is extremely vital. Then, based on the new B and M that we have got, what actually do we have to do? So new B and M we have got. That means we have got a new straight line. You can assume in this way. So if you have got a new straight line, you now have to calculate average error based on the straight line, because if you have a new straight line, you can easily calculate the predicted y for each and every axis. So that is what this compute error for line given points does. That already you have seen here. So based on that, we will get an average error. This is the error. And you see here, I have just to show you how it is running. I have written that if I is I% 100 equal to 0, that means for every 100 iterations, it will show what is the error in that particular iteration. Okay, just to show you. And at the end, this gradient descent runner, after that amount of iterations that we have decided, it will finally return the final B and final M, that is the final intercept and final slope. That is the equation of the straight line that basically you wanted. Now, if you have that, obviously just putting value of any unknown x, you can get the corresponding predicted y. But anyway, right now finding unknown x, finding some new y for unknown x is not my goal. My goal is to show you how, is it really error is decreasing and how it is decreasing. So it will be very interesting, I think. So let's see. Let's run one by one. So first I will, let's run this part, even this line, even this particular function and this function, and all obviously this particular line, you can even off this line. Sorry, not this one. So they don't need to print the points, just point and keep decided. And now we have done one thing, a very important thing actually, that already you experienced in my previous classes, that is scaling, right? Because already you have seen the points are in a very long range, so it's better if you do scale and keep in a range between 0 to 1. So it will be easier to, not only easier to train, but also it will be easier to get the good model as well. So let's do one thing. Let's scale it here. Okay. So these points scaled, if you print, you will see everything has been scaled down in between 0 and 1, I hope. So let's print once here, and you see all the data that you had is actually scaled down within 0 and 1. Anyway, so printing is not very important here. Now here it comes. We decided that learning rate we will keep at 0.01. We have decided some initial value of B and M. Instead of 0, you can keep some other values as well. Then we have decided the number of iterations, say 1000 times. We will continue the changing the M and C. Basically, so if you can remember the plot of the error, you started from a point on the top. So 1000 times you will get a chance to go at the at the optimal value of the error. And then actually I have just written some initial b, and then I've called this gradient descent runner function here, this one, which is basically doing all these things. So let's do one thing. Let's run this particular part. So if you run this, you will see it will start printing the errors, and you see from 2.247, if you see the errors, it's basically decreasing. You see, it started from 0.247 something error. The next error becomes 0.025, next error 0.022, then 0.021, 0.020. In this way, you see the error is decreasing gradually, just like that we have seen in the presentation. Interestingly, if you change this learning rate by very low learning rate, for example 0.001, okay, the learning is very slow, should be. So let's do what will happen. Let's see. You see, we started from here. Now just see the difference. What you had in the next time of 0.025, it was 0.02, but here it is decreasing like 0.25, 24, 23, like this. So it's very slowly it's decreasing. So you require many more iterations maybe to go to the optimal state, right? Similarly, if you go for a very high learning rate, say for example 2, I've given a very high learning rate 2. So let's see what will happen now. If I do, you see is 4.5, then 1.81, then next become again increased. It's not decreasing, and at the end somehow it becomes infinity. It's actually because of some some runtime issue, maybe because of that. But whatever, my point is that interestingly, you see initially error was 4.05, then it decreased 1.81, then it again increased. So what happens? It's like you can assume it's basically trying to oscillate between the some error values, but never reach to the optimal value. Will never reach. Even instead of 2, if it is 1.05. Just I'm checking. I don't know what will happen. Let's see. Yeah. You see, the error is not at all decreasing or increasing, you can say. It's basically oscillating within some particular range. You see, initially error was 0.70. Very good. Suddenly it increases, again increases, and second again decreases, again increases. So this increasing decreasing oscillation will keep on moving. If we have this very high in learning rate. So now I hope this is very clear to you that what will happen if we have a very high learning rate, as well as what will happen if we have a very low learning rate. And that is why this learning rate will become very vital when we will basically create any model, not only for linear regression. Okay. Anyway, so this is a very small example. Basically, we have discussed on the gradient descent part. But let's do one thing. Let's now try to see exactly, with some package, some Python package, how we can implement linear regression.